Good afternoon, everybody. We're going to get started in about 5 minutes. I just wanted to let everybody know. Good afternoon, everyone. My name is Drew Burns, and I'm the Executive Director of the Slag Cement Association. I'd like to welcome you to today's webinar, Demonstrating Resilient Concrete Results with Slag Cement. We are glad you could join us. The video recording and PDF of the presentation you are about to see will be uploaded to the SCA website, slagcement.org, following today's webinar. Attendees are in listen-only mode. You may ask questions using the dialog box in the GoToWebinar software. Our speaker will be happy to address questions at the end of the presentation. The learning objectives for today's webinar are as shown on the screen. They are also listed on the SCA website with the webinar series information. Now I'd like to introduce our speaker. Shawn Kalyn is a technical services engineer with St. Mary's Cement and has been with the company for more than 15 years. He received his degree in civil engineering from Ryerson University in Toronto, Canada. His responsibilities include providing concrete solutions to cement customers and the promotion of concrete and cementitious products. Kalyn is involved with the Portland Cement Association Sustainability Committee, ICPI Technical and Education Committees, the SCA's Great Lakes Regional Task Group, and our Technical and Marketing Committee as well. He's also involved with the MIT Sustainability Hub. And now, Shawn will begin today's presentation.
Hi, thanks everyone for being in this webinar. First, we're going to start with the term resilient and resilient concrete. One thing it is to be durable, yet we're mindful of long-term global environmental impacts and changes. So like according to the Resilient Design Institute, you'll see the international design of buildings, landscapes, communities, regions in order to respond to nature and man-made disasters and disturbance of well as long-term effects due to climate change and other impacts. Next slide. One disclaimer is as we're looking into doing green buildings and green infrastructure, one of the things we got to kind of look at is the short-term and the long-term goals of that project. We may need to change and vary, like for example, in this picture, you're going to see whether it's done in the summertime and the wintertime. So kids in the winter are going to be wearing a lot different clothes than they are in the summertime. So we got to adapt to those goals and make sure that our goals are going to work out correct. For example, you may be able to use high amounts of slag in some cases, but there may be some trade-offs on how long it can take for the project to go in the strength gain of those products. Next slide. Understanding carbon. Today's focus is going to be on understanding carbon and the EPD and the environmental side impacts of the durability aspects and of slag cement. So with that, the next ones you're going to see in the next webinars are going to be more on the physical durability impacts and so forth. So this one's going to focus more on how slag helps with the environmental side of those impacts. So to understand carbon, one of the things we're going to look at is operational carbon. Operational carbon is the energy that's needed to heat, cool, and power a building. Most of the operational carbon is in that location. So if we're looking at carbon as a whole, most of our energy use is going to be in the operational phase of a building or infrastructure. The next thing that we're going to look at is embodied carbon. Embodied carbon is the greenhouse gases that are emitted during the construction phase of the building, as well as the materials used in the construction of a building. Term carbon is to indicate greenhouse gas emissions, so it's not just CO2, but you're looking at methane and other equivalent types of CO2. So most of the times when we hear it, we're going to hear CO2 equivalent. So that's including all of it. The next thing we're going to look at is environmental product declaration. Environmental product declarations are what we like to say is the executive summary of an LCA assessment of a product or of a building aspects of it. The next one is when we make the product declarations, we use what's called product category rules. There's certain rules that are made from ISO. From those ISO rules, then each product kind of makes its own rules based off of the ISO rules that are there. Once that product category rule is done, then we go into what the next thing you see here, which is life cycle assessment. Life cycle assessment is to evaluate access and improve the environmental burdens associated with the process, product, or the activities identified using the quantitative energy, materials used, waste streams, and so forth that are going to impact the environment. Next slide. What we're seeing now, and we've been seeing this for quite a few years, but we are seeing more of it happen now, and it's being more, is regards to transparency. So in our buildings, we are looking more for transparency. And as you can see on this slide, there are multiple different ways of doing it, whether it's building codes, whether it is DOTs, whether it is accreditations such as like USGBC, where they may have a checklist or something to look at. And then a bunch of them is also like Architecture 2030. Next slide. Architecture 2030, we kind of before we're looking at certain areas like increase the recycled content, or let's look at FSC wood, or certain things like that. Now it's kind of going to more of a holistic approach and looking at the carbon emissions in this example. There are a lot of other environmental impacts, which we'll kind of show later on, but the one that seems to be gaining a lot of ground is carbon equivalencies. So one of the things is Architecture 2030 has been trying to reduce the use of fossil fuel consumption, but also CO2 equivalencies in regards to the embodied of the building itself, because they find that if they want to become carbon neutral by 2050, they are going to have to look at the embodied energy and the energy used to making of products. Next slide. Also, what we've seen happen is not only are they going from the Architecture 2030, meaning going from buildings themselves, but we are now seeing the same movement move towards cities themselves. And you've got a bunch of cities such as listed here. There's 22 cities now. Last time I updated this slide was a couple months ago, and now it went from 18 to 22. What we're seeing is you have cities at certain region areas that are now looking to reduce their energy consumption, water, and transportation emissions to help reduce CO2 impacts. Next slide. Here's a good example of it in the City Vision 2030, like I kind of talked about before. This was from Aaron McDad. We are making global processes in reduction of operation emissions, but yet even with the operation emissions, they do realize that if they want to phase out fossil fuel emissions by 2050, they will not be able to complete this without looking at the embodied carbon that are in the materials themselves. That's why we are starting to see this, and that's why this presentation is on today. Next slide. One of the things that we see, and we're starting to get beat up sometimes on the concrete industry, is they go and they say concrete has one of the most amounts of CO2 in its product and its use. Now, if I look at this slide here, you're going to see this is a logarithmic slide, and you'll see that in this, there's other materials in there, but concrete as a whole is the widely most used material in the world. So since that's the case, yes, there is going to be a lot of carbon emissions due to it just because of the sheer amount of volume of concrete that's used. Now, if we go on to the next slide. But one of the things we got to look at is when you put it into context, is this slide here is going to show the embodied CO2 that's used for manufacturing of concrete versus the embodied energy per kilogram of material. So when we look at this, we see that when it comes to the embodied CO2, concrete has a very low embodied CO2. So if we are getting beat up in other industries, such as say timber or so forth, saying, yes, they have the better green movements on it. When we look at this kind of data, we're seeing that if we move away from concrete to other type of products, we may actually increase the amount of CO2 that's going up into the air. So we got to be very careful on how we look at it and so forth. And can we reduce it? Absolutely, we can lower our CO2 emissions because we have a bunch of tools and levers that we can work on that is also showing that. And you'll see that if you look in this slide where you see the cement section. So if we go from Portland cements to blended cements, such as using slags and fly ashes, that's going to help reduce that information, as well as other things that are starting to occur. So next slide, how do we accomplish this? Well, there's three ways. You want to use SMART, so do the materials you're using need to be new, or can you use recycled materials such as slag cement? It comes from the steel industry process when the slag that is put to the top is then exposed of, which would have been waste. We now process it into granules and then grind it into slag cement. So that would be a smart use of the material. Building smart, looking at using materials and resources and the best product outcome. That's when we're starting to look at these life cycle impacts, or looking at, for example, if we're looking at a concrete one, can we use more slag in certain mixes versus other ones to impact and reduce those emissions? And then the last part is to buy smart. We want to buy smart. We want to look at the EPD aspects of it, but we got to also look at it from a regional standpoint and where it's at. So for example, we may be able to find that, okay, this concrete here that is in Washington, DC looks great, but if I'm in Spokane, I can't gonna get the product material from there all the way to there. There's going to be a lot more emissions and so forth used from just the traveling and transportation of that product. So we got to look at it smartly and make sure we're buying smart. Next slide. So what is an EPD? Well, the EPD, kind of like what we were talking about when we were saying the definitions, we utilize or create a product category rules. Once those product category rules are made, then they conduct what's called an LCI, or an LCI, which is the life cycle inventory information gets all collected, and then it's verified into a life cycle assessment. From that life cycle assessment, they make up the nutrition label, which we would call, which is basically the impacts of what was in that LCA. So without having to provide the full LCA information, which could be hundreds of pages, you're seeing it in a couple, 2, 3, 4 pages with the data of what you're looking for. Then once the EPD is created, sometimes they can be just self-reported, or they may go through for third-party verification where they are verified by someone else, third party, to verify and look at, yep, were the inputs they used correct? Did they follow the product category rule guidelines? Yes, they were all followed. Then once that has been approved, then a lot of times it will go to a program operator who will publicly display on their website, such as ASTM or NSF or CSA, where they will actually have your EPD publicly listed. So that way architects, engineers, or other designers who are looking to see what the impacts are, they can go and get that publicly. Some of the impacts that we're going to see on this, what we call a nutrition label, is primary energy, global warming potential, ozone depletion, acidification, eutrophication, and creation of smog. Other things you may also see is water use, the amount of waste, the type of waste that come about. Next slide. So for an example, when we look at the slag cement does have an industry-wide EPD. This industry-wide EPD was done in 2014. And like we were saying before about how you go through the process, the Slag Cement Association currently right now is working on their product category rules. So I would expect by 2021, which will be a busy year, you'll see that the new industry EPD for slag cement will probably come out next year in 2021. So if we look at the information that's on an EPD, this is kind of what we're looking at. And you're looking at it from what the raw material was, the material used to extract it, the transportation, the manufacturing, and then the whole combined information on it. So in this case here, we'll see that the raw material was very low. And the reason why is because slag cement, the granules that come into it, all those emissions in that were made in manufacturing of steel. So we see the raw supply material information is very low because that's just processing it and making it now into the granules. Transportation, that's taking it from the steel industry to where it's going to be manufactured. That's where you're seeing those information and details into it. Then you're going to see the manufacturing process. And you see these numbers are going to show for what is required under the product category rules. And kind of like I was talking about before, there's the material resource consumption, non-renewable materials, renewable materials, recovered materials, as well as fresh water. And then in waste, sometimes you'll see hazardous, non-hazardous. Next slide. So how does this slag cement fit into the picture? What we're going to talk about is how slag cement reduces the carbon footprint of concrete, what other durable benefits slag does contribute to cementing concrete. We'll go a little bit into that, but that's going to be followed more into the following webinars that will come up in the next month. And how do you use the LCA tool to convey these benefits, and how slag can be used in the lead credits and how we go through it on the materials aspect of it. Next slide. This is an example of the Portland cement industry EPD. So if we look at the top there, we see the global warming potential for cement, and we see that it's just over 1,000 kgs. If we looked at that industry EPD for slag, we saw we were at 146. So as we are looking into the concrete end, we are supplementing the slag cement in replacement for the Portland cement, which we can see is going to lower per ton the amount of CO2 as well as the other environmental impacts. Next slide. One thing that you're going to see that's going to be gaining ground is also a product called PLC, and we're starting to see specifications starting to look at using this and so forth. But an example of here is when you take in Portland cement, and now they've introduced the use of limestone, which was not calcinated. And as you can see in this, we went from 940 down to 855. So we are seeing changes not only on the cementitious side, but we're also being able to make those impacts and changes on the concrete side and the materials we choose to use. Next slide. When we go into looking at slag compared to Portland, slag, or PLC, we're going to see that when it comes to global warming potential, slag is obviously a lot lower. When we look at it from a primary energy consumption, we are going to see that it is lower. Next slide. One of the things that we do see is with using of slag, it does give us a lot of synergies when we're using it with PLC, or even when we're using it with ordinary Portland cement. We're seeing a lot of benefits, not only from the energy side of it, but we're also seeing it from the durability aspects. We're seeing it from the workability aspects. We're seeing it from the color reflectivity aspects of slag cement, and a bunch of other reasons for using slag. When we look at the global warming potential, depending on the cement we're using and so forth, we look at this, we're using 100% cement, we see the global warming potential is going to be a lot higher than as we reduce it with using slag. One of the other things is also on the non-renewable resources. Because it is a waste product that was now reused, we can see that we're not using up our natural resources as much. Also, we see the primary energy consumption per cubic yard will also go down in that concrete. So for example, if we take a 3,000 PSI mix design, there's a possibility that we will see 100 kilojoule or 100 kilograms of CO2 reduced, 200 kilograms of natural resources were saved, and 500 megajoules of energy was not used. Next slide. One of the things that we also see too is if we're looking at it from not only just the ready mix industry, precast, en bloc, and other concrete materials can use the use of slag. In this case, this was a study that was done by the PCA using CTL. And as we can see, there's different cementitious amounts, water, coarse aggregate, and fine aggregate. But if we go on to the next slide, we will see that in every case, when we went from 100% Portland to 35% slag replacement, or even 50% slag replacement, we are going to see the CO2 reduction in the materials. Next slide. Now, when we go to concrete and the concrete reality, we're going to look into this. You're going to see this kind of graph more so when we go into it further on, because that's part of the Slag Cement Association's LCA tool. But in this case here, we're going to take the DOT example. In this case, it is Ohio DOT. Back in 2012, they had went and switched from being prescriptive base mixes to performance based mixes. So if we just look at their bread and butter mix, which would have been their Class C concrete, it consisted of 600 pounds of Portland cement, and they had some variations of it. If we look at that first column there where it says climate change, CO2 equivalents, we can see that when we've gone to this now performance base where they're allowing the use of slag or the variations of it, that we can see that the global warming potential has gone down. So the Class C, if it was 321, we now see that we've dropped it when we're using this QC1 with 450 pounds and 150 pounds of slag. It's now down to 260 CO2 per yard of concrete. That's one of the things that we are starting to see a lot of when it's coming into specifications or designers looking at it, is they may actually have some targets that they're looking at, and how do you know what CO2 amounts you have? Next slide. So now we're going to go into an example of a low body carbon concrete using slag cement. So in this scenario, we're going to have a ready mix producer and a concrete flatwork construction company need to find a way to lower the global warming potential on a retail shell and core box store in Avon, Ohio. Just use that as an example. The designer has some already thoughts on what they want to look at reducing the whole CO2 and the whole building. So in this case, they're looking at the footings, which is 3,000 PSI, to have a maximum Portland allowed of 456 pounds, or that the global warming potential must be 303 kgs per cubic meter. Or on the 4,000 PSI, they're looking at 503 or 338 pounds of CO2. So they've kind of got themselves limited to what they can do on what is needed. So the ready mix producer and the flat work finisher need to come up with ways on how do they get to those numbers or show lower numbers. Next slide. So what we do when we're using the slag is it's all going to start off with, when we get to using the tool, is we're starting off with the industry EPD information. And if you want to get the SCA's industry EPD, you can either go to ASTM or you can go to the slagcement.org. The future industry EPD will most likely be using NSF, where it'll be on the NSF website. Next slide. Now, when we're looking at the life cycle for ready mix, this tool is where it's used the Slag industry EPD as well as the NRMCA's industry EPD benchmarking information. The industry for the NRMCA just completed the 2019, their current version. This calculator was version 2. So while it is not exactly the perfect accurate one for now, it is still a good tool to use because it's going to give you an idea when you're looking at what are ways that we can reduce our amounts of CO2 and give you some ballpark numbers. Next slide. Here's an example, like we were saying originally in that question, where did those numbers come from the limits on cement or the limits on the global warming potential? We are starting to see not too much. This is starting to happen more towards California, and this is actually one of the specs that someone was trying to introduce. So this is where you have a designer that's telling you this is what you're going to use. And in some cases you could, in some cases you can't, depending on what product is and what application these concrete mixes are to be used for. So this shouldn't really be used, but it should give you at least a good guideline to try and work towards getting lower numbers. Next one. So what are we going to do? We're going to use the SCA calculator. We're going to put the inputs on the tab. So on the customer tab, we're going to enter in custom mixes. So we can add in this tab. There's up to 10 boxes where we can put it in. We're going to type in the mix ID, the type of mix strength class we're going to look at, the type of mix proportions, the multiple mix classes can be entered into the customs tabs, which will populate comparisons to the benchmark. Now this benchmark we're going to see is going to be the benchmark of the classes for the NRMCA EPD information that they had as their benchmark. So they would have a classification for like 3,000, 4,000, 5,000, 6,000, and then they had an 8,000. So when you're looking at it, if you had a mix that was 3,500 PSI, you're going to bump that to the 4,000, or maybe you're going to go down to the 3,000 It's not going to be perfectly accurate, but that's the class ranges that they have. Next slide. So when we start to enter in these mixes, we're going to see that you've got the custom mix tab that we're onto, and we are going to type in our mix IDs. So on a job, in this case, we said we're going to have a footing mix and we're going to have a floor. In this case, we're putting in the maximum 456, which is what they said for the 3,000 footer. And then we also put in a formula that's going to show the 4,000 floor at the maximum 503 cement. Now we're also looking at using Slag into this. So how is Slag going to help us and improve this? So in the footer, we used one that was going to be 25% Slag. We also looked at using a 40%. So depending on the time of the year, the application of where it's going on to, the region of where we're at, we may be able to use higher amounts of Slag as the temperatures change. So slag cement likes heat. So if there's heat or curing being added to it, you can use more amounts of slag into that mix. So that's why in this case, we added 2 in there just to see. So because we said this was in Avon, Ohio, we could be pouring in the winter or we could be pouring in the summer. So to try and optimize, that's why you're seeing these 2. For the slabs on grades, a lot of times we may not see a higher replacement of slag just due to the fact of the time constraints on setting times and finishing work that may be required by the contractor. So in some cases, you may not want to be at high amounts due to the setting times. And with that set times, it may actually delay the amount that that project can go. Go on to the next slide. So now in comparison to the benchmark tab, this will show us the environmental impacts compared to the NRCA's industry EPD. So if we go on to the next slide, when we took those materials before, we took those benchmark material ones and we took those mix designs and we put them in, this graph here is going to show you the environmental impacts for climate change, ozone depletion, acidification, eutrophication, smog, and then the renewable energy resources. We see this on this chart, and we can see that that first mix, that if it would have just had the straight Portland cement into it, obviously is going to be more than what the industry benchmark currently was back when they did the version 2. When we look at using that 25% slag, we can see there's a considerable drop in there. And from the climate change aspect, it's saying 91%. When we look at the mix 3 with 40%, we're seeing now we're down to 79%. For the floor work, we're seeing that we got a 15% reduction. And these all come in handy as we get further into the lead aspects of it. And I'll explain why later on. Next slide. So using the SEA calculator, we can also, if we wanted to look at it quickly, if we already typed in the mix design section, if we already put in the custom section where we put in the benchmark that we're looking to use for the project, then we can look at different amounts of slag substitution. If you can go to the next slide. In this one, on this tab, we are going to be able to adjust the amount of slag by just looking at this column up here where you're seeing the slag cement up on the top and it says adjustable percentages. We can raise or lower the amount of slag, and then we can look at that graph that's next door to it and on the right hand side and see, compared to the benchmark that we need to use for this project, are we getting lower or is it going to be higher? And that way you can use that to see, okay, what's the minimum amount of slag I need? Or is there a way that I can improve and increase the amounts of slag? And by talking with the contractor as well as the designer, you guys can get together and make it as unique as possible to try and get the lowest amount. Because remember, like I said originally, we need to do the trade-offs not only of what we need done for the job site now, but we're also looking at how it's going to impact it in the future and how it's going to impact our environment in the future. So we kind of have to gain all those together. One of the things that you're going to see in this tool too is up on the top right-hand section, you're seeing a section that says region. So in this case, you're going to pick the region of the country you're in. And the reason why you want to do that is two reasons. One is these mixes are based off of a regional area. So in this case, it's the Great Lakes Midwest. The way concrete is made in the Midwest is going to be different than the way it is made in Florida. So there could be higher or lower amounts of cementitious or sands or stone and so forth being used into it, or even the types of sand and stone. Because as you can see on the left-hand side, we have a bunch of material options that can be used. Also, the other impact, which is not really seen on the concrete side, but it really impacts us, is the energy grid that's being used. So depending on where the energy grid comes from, can very change these same numbers. So for example, if we are pouring concrete and we are pouring concrete in Sarnia, Ontario versus pouring concrete in Detroit, Michigan, we will have number on that CO2 limits because the energy grid that they're looking at will be different. The Ontario grid, which now does not have any coal burning power plants, is going to show a lot lower on fossil fuel reductions information versus the Michigan one, which still has that. The other part you can also see is hydroelectric or nuclear are not going to have as much fossil fuel use. So as that fossil fuel use goes down, we also see that our CO2 equivalents will go down. So depending on the energy grid that's being used, that's going to impact our numbers, a lot of the factors that we don't have any control over. Next slide. Now we're going to get into LEED and going into the old and new versions. So from versions 1 to version 3, when they looked at it from the materials side, you kind of got credits for single attribute points, such as if you had recycled content in your concrete, you would get so many points. If you had FSC wood, you could go towards getting a point. They've now kind of tried to do that and make it into a holistic approach. So yes, it can be very confusing and it's very hard in some cases, depending on, especially if you're the contractor, and in some cases, the ready mix producers or the concrete producers may not have the actual information of whether it's version 3 or whether it is version 4. But I'll kind of give you some little tips on how to know the difference between which one they're looking at, because a lot of times they don't even know unless they send you the information in the documentation. But we are going to see that under the version 1s to going to version 4, that we went from those single attributes, combining a bunch of those single ones now into single credit applications, which can make it confusing. Next slide. One of the things that needs to be done at everything of every LEED project, which one of the biggest questions I always get is the designer assumes that the cost of the material must be the cost of the materials delivered to the job from the concrete producer, but that is actually not the fact. This is actually written and from LEED itself. So you'll see that when they're looking to calculate the material costs, you are looking at the cost of materials of the actual material cost or the default material cost. Here's the thing that's neat about it. The actual material cost is the cost of the materials being used on the project, excluding labor, but including delivery and taxes. Saying the delivery and taxes shows you that this information has to come from either the subcontractor who's providing the cost to the owner or the general contractor who is providing the cost for the project. So also under LEED, which in some cases, depending on the concrete being placed, that there's also a default material cost. So in some cases, some of the materials that are being used on the job, they may not know what the labor costs were and the material cost for it. So there's an alternative method, which is you can determine the total material cost that is used to calculate it and calculate out 45% for the total cost of construction. So in some cases, materials may be less than the 45% and the labor be more. So in some cases, looking at how you're going to look at the calculations, you may be better off to use the default cost versus the actual material costs. But in any way you look at it, most of these material costs that you have to get has to come from the contractor, not from the concrete producer. The concrete producer, though, can help out by giving some tools such as information of what was the material that they used, and give an Excel spreadsheet that then that way, real easy, the contractor can put in the amount of yards and the contractor can put in the amount of weight or the cost of the materials into it and figure it out by cubic yard or by, if it's block, figuring it out per sectional unit. Next slide. Here are the material resource credits that are now in the version 4. So we're going to see building life cycle impact reduction. We're also going to look into today is the product disclosure and optimization using EPDs, as well as sourcing of raw materials, material ingredients. Those are the 3 that we're going to focus on today for this presentation. One thing I also wanted to mention too is that LEED is now kind of going away from 4, but they're now doing a beta project, which will be 4.1, because they realized when they went from the version 3 to the version 4 that version 4 wasn't really being adopted. And in the material side, the credits were not being used and they were very hard to achieve in some cases. So what we'll see in the next slides is the difference from 4 to 4.1 and how it kind of impacts whether it's done one way or the other. One thing that all the projects that are V4, they can substitute that credit to the 4.1 credit should they choose to. Next slide. So right now we're going to start with the credit of environmental product declarations. So like we showed before, we showed the industry EPD one. So in this case, if you have a product specific declaration one, which means that you self-declared it, but you didn't have anyone third party verify it, that one is worth 1/4 of a point. If you have an environmental product declaration that's an industry wide, that one is worth 1/2 point. If it is a product specific one, so now we've gone from the Slag Cement Association's industry one and now made a product specific one, then that would be worth a full credit. One of the things that you're going to see is in this one, the neat aspects about concrete is that slag cement is only a component into the concrete. So on a concrete floor, we might have 3 EPDs. We could have the EPD for the Portland cement, we would have the EPD for the slag cement, and then we would also have a possible EPD for the concrete as a whole. So that in this case would be 3 EPDs that could be used towards those credits. Next slide. So when we go from the version 4 to the 4.1, we're seeing that we want to have 20 permanently installed products. So like we said before, when I was talking about there was 3 that could be in the floor mix, there could also be 3 the same ones that were now also used in a footing. That would be considered a different product when you're looking at the buildings themselves. So now under 4.1, because they thought it was too hard to get the EPD information in the original 4, they've dropped the threshold from 20 permanently installed products down to 10 installed products. For the industry EPD, which used to be worth 1/2 point, is now worth a full point in 4.1, and the product specific ones are now worth 1.5. Next slide. Okay, we've gone from the having the EPDs or just showing the EPDs, which is one of the credits that LEED was looking to do. As we start to move on and move forward on stuff such as the Architecture 2030, we're now looking at benchmarking and looking at how does that EPD and how does that material that you're bringing to the job site, is it going to be higher or lower? And we're starting to see now that we're getting into the benchmark phase of construction, where we're now starting to see we're trying to reduce the global warming potential as well as the other environmental impacts. How are we doing it, and are we seeing it going lower? Are we raising the bar? So in this credit, we're going to see in option 2 It's the multi-attribute calculation. So in this one, they want us to have the third-party verified EPD, compare it against the categories for that material we're looking to use, and see that we are lower in each one of these credits. Under the version 4, it used to be 50% of the total cost of all the permanently installed products on the project. We're going to see now under the new version 4.1, they've dropped that threshold down to 10%. One of the things that is an easy way to tell if you're in a version 4 versus a version 3 project is a lot of times you might get asked the question, I need your lead letter or I need your lead information and I need it within 100 miles. In the old version, we used to see under versions 1 to 3, we used to see that the mile range was 500 miles. Now that's been dropped to 100 miles. This credit is now hard to get because it needs to be extracted, manufactured, and purchased within 100 miles. And currently, right now, they're saying that if 90% of the material is in those 3 categories, then they will give you the extra credit. In the past, under the old versions, it used to be its own separate standalone credit. Now, the way they've made it is all the credits, if you have regional material in it that meets or suffices that within 100 miles, then they're going to give you double the amount of value for that material. Next slide. So when we look at 4.1, like we said, we saw that the cost requirement got lowered from 50 to 10%, or they have the option of using 10 products. So for example, if we had footings, we have walls, we have columns, we could easily on a project, especially if it's a school type of project or an institution type project where a lot of concrete is used, we could see a bunch of items being used into that. Also, they could do it by tiers. If you go to the next slide, they're showing when we're looking at the global warming potential impacts, if we see a 5% reduction, or we see a 10% reduction, or a 20% reduction, when you're comparing them from the industry-wide EPDs to the product-specific ones, we're seeing these values go down. Remember before when I told you we're going to be looking into the SCA calculator and seeing those reductions and why those numbers mattered when I was talking about that 79%? Here's where an example that it shows you. So in this case, we would know that we would at least get the 10% reduction on that, which helps gain their points. Next slide. So going on that, we're going to use this as an example. This is a different project that was being used, but in this case, using the SCA calculator, we have footings, we have slab on grade, interior concrete, exterior 4,000, 4,000 stair pan mix, 4,500 exterior concrete, a lean concrete, and then a lightweight concrete. All those were put into this aspect, and we're looking at comparing it to the industry benchmark for the NRMCA. And in this case, it was using the Great Lakes as the region. So when we look at this, we could see that mix 1, 2, 3, 6, and 7 would go towards that credit of the multi-attribute application showing the lower numbers. And when they do that, they're not only just looking at the global climate change as one, they're looking at making sure that at least 3 of these environmental impacts are lower than the industry average. So as we can see in here, that's the case. One thing to note on this mixes that you're looking at, only one of these mixes actually used slag. And if you look at mix 6, it actually had the highest cement content, which was 600 pounds total cementitious with 25% slag. If we look at mix 1, 2, and 3, and 7, all of those mixes were using fly ash. So we can see that as we use slag, we lower our numbers. If we look at mix 2, that was with 25% slag with 520 pounds total cementitious. So we look at that number and we look at mix 6, we still see that slag at the same amount at 25%, but actually with a higher total cementitious mix shows lower numbers. So we can start to see now when we're looking at mixes that we might be better off in some cases to use it as a slag versus using a fly ash or so forth, because we can get into the more workability, or maybe in some cases we want some more paste in that mix because you need it for the finishability and the workability. So we can really now start to look and narrow down what is really the best for our customer. Go to the next slide. So now we're looking at building life impact reduction. Now this is the whole building. One of the things that's on that SCA calculator, and one thing we are starting to see now, is there is a lot of work going towards looking at the total building impact of CO2, like we saw from Architecture 2030 or even the City 2030, where they're now looking at the embodied carbon and how it got brought there. They're looking at all the materials as a whole. So one of the things that's on that tool is there is an assessment that shows a 5,000 or 5-story building with 50,000 yards of concrete typical on it. And they're explained to see how the product would work benchmark versus the ones that you had. So if you put in the information on the regular materials section, you are then going to see, you type in the amount of yards into that tab, and that's going to give you the whole building impact assessment. One of the things under lead that we're looking at is on the whole impact assessment is they want to see at least 3 categories where there's a reduction in the environmental impacts. They're basing this on 60 years. As a concrete industry, we would rather see it as 100 years. But when it comes to life cycle assessments on buildings, most of the times they're using 60 years. Next slide. When we go to version 4.1, we've seen that they still have that whole building aspects, but they've now increased the pass or the amount of points that can be used. So we're going to see if you did that a whole impact assessment tool and did it on the enclosures, it's worth 1 point. If you've done a 5% reduction, it's now worth 2. If you've done the 3 points for 10% reduction of those materials. Next section. In the SCA calculator, this is just showing us that tool that I kind of was talking about, where if we type in the mixes that we wanted to use, and then we look at the very top there, we're going to see the amount of yards that were used for each one of those. Then the designer or the contractor could say, okay, on the floor, we had 800 yards of concrete. And by putting all that in, that's going to give you the total assessment of that building. So in this case, we can see that with the amount of yards of concrete that was used in the footers, slab on grades, the interior, and the lean concrete and the lightweight concrete that we used, that the total impact for the building was at 89%. So that 89% would show us that we are getting a credit of at least that 10% because we're at 89 versus 90. So we're seeing the values in that. Also in that calculator, it also adds in the non-concrete impacts such as steel, glazing, insulation, wood, etc. that could be used on that project. And then they make it with the amounts proportional to the amounts of yards of concrete that was selected for the project. Go to the next slide. So one of the things that we're looking at when we're looking at the sourcing of raw materials, now this is kind of going back into that old credits under version 3, where we're going to see the recycled content. We're going to also see a new one now, which was on social sustainability. We are going to see the impacts and the intents of that one. So go to the next slide. One of the things that if you are a supplier, and a lot of times the suppliers of slag cement actually have a global reporting initiative where it would be third-party verified sustainability report. That sustainability report could be used sent in to the ready mix producer or the contractor and say, okay, yes, this company XYZ does have a corporate sustainability report. Here's a link to their report. That will give you a credit towards this. And in this case, they're looking for 20 permanently installed products from at least 5 different manufacturers. So like we were talking about before, where there may be multiple concrete materials used on that job site, such as block, flooring, precast walls, that cement and slag cement could be used in all of those. So they want it to be from at least 5 different manufacturers. So it couldn't be all from one block manufacturer or for all from one ready mix producer. It would have to be from multiple ones. Next slide. Now we're getting into the extended leadership extraction processes. This is the option 2 of the credit. And in this case, they are looking for material reuse, recycled content as another one, or looking at USGBC programs or other programs that have a leadership extraction criteria process. The NRMCA is trying to get one approved right now, kind of similar to if you have an SSC wood, that you would be able to get credit for it. And it's looking at your leadership extraction criteria stuff. That has not been completely vetted through yet, but that's what they're looking at. Now, if we look at the bottom of this credit section, we see that 100 miles again. So we see, like I said before, all of the product in the material resource credit areas, we are going to see that if the product is within 100 miles, that you're going to get a value of double the amount or 200% contributing towards that cost in the calculations. Next slide. So on the environmental impacts of the whole building life cycles, actually before we get to this, when we get into the recycled content, slag cement would be considered 100% pre-consumer. There is a pre-consumer and a post-consumer. Post-consumer is considered when you have a product that was consumed by someone. So if we had a Coke bottle and we drank from the Coke bottle and then that Coke bottle ended up being used as a raw material in a different used material, then therefore that would be considered post. Pre-consumer would be when it's gone from industry to industry. So in the case of slag cement, the steel industry would give us the raw slag that would then be made into granules, which then becomes into Portland or then becomes into slag cement. So that's kind of the tip-offs for when it comes to the recycled content. But slag cement is 100% pre-consumer. So now we're going into a couple of the end slides. Environmental product declarations. Go back one, Drew, for a sec. When we're going and we're reassessing it, we're feeding into the whole building assessment. So the embodied carbon is going to be used from the environmental product declarations. Then we're going to have the whole building life cycle assessment that's going to look at that. Then there's also going to be tools and software that's going to look such as the Athena Impact Calculator or Tally that then adds all that information such as from the steel, the wood, the concrete, the blocks, everything, all of that from the embodied product from the extraction to the location of the materials being constructed will all be put into that portion. Once that's done, then they will look at the whole building aspect of it and they'll look at the operational energy that was used. Then after the operational energies and so forth that's being used on that building, the life cycle of that, they'll also look at the next life cycle is when the building is no longer being used, is it going to be demolished? Is that building going to be repurposed? Or is it at the end of its life? So the first part, such as what we were looking at for the environmental product declarations for the industry and product specific ones that we're seeing right now, we're seeing it from cradle, meaning extraction, to the finishing of the product to the gate of the manufacturer's door. We're now going to be seeing further on, getting into the construction phase, getting into the use phase, and then getting into its end of the life. So on the end of the life, you're going to see it go from cradle to grave. That's why you'll hear that sometimes. Next slide. It's not moving. So with that, we're going to go into the next thing is the slag cement and concrete specific LCA. I don't know if you guys can see this or not because I don't think the slide is moving, but you'll be able to use, there's a free download from the SCA that you can go and download the Ready Mix concrete life cycle assessment calculator for slag cement. Also, the calculator lets the designers enter custom mixes, substituting varying amounts of slag through a simple dashboard, allowing them to compare different mix designs. The tool also allows the input of mix designs for hypothetical whole building life cycle assessment scenarios and step-by-step availability to use on the websites. Some of the resources that are also part of this is there's a good resource to look at is the Carbon Leadership Forum. They got recorded webinars and slides on the embodied carbon and networks and how to look at that information. LCA presentations can also be looked at. We've got some of them on there. And then there's also a link to the LCA practice guide by the Carbon Leadership Forum. With that, would like to say thank you. And Drew, I'll let you open it up to questions. Hello, Drew. Any questions? Is the upcoming webinars. The upcoming webinars that we're going to have is going to be the role in slag cement in creating sulfate resistance concrete. That's going to be presented by Ryan Betts of Argos on July 9th at 1 p.m. Eastern Time. Then the next one on July 23rd at 1 p.m. Eastern Time, it's going to be ground granular blast furnace slags, rapid reactivity testing and effects on varying replacement levels on the paste of properties. And that's going to be presented by Shikavimura Brahmahathan of the University of Miami. And then on August 18th at 1 p.m., they'll be mitigating alkali silica reaction with concrete with slag cement, presented by Keith Madre and Clayton McCabe of Argos Cement USA. With that, would like to thank everyone for being here. Have a great day.